Greetings. In this video, I will aim to provide a digest of the method self-distillation with no labels, or Dino. This work was introduced in the paper Emerging Properties in Self-Supervised Vision Transformers by Caron et al. And was published at ICCV 2021. This is an outline for what we will discuss. We will begin with the motivation for this work. Next, we will talk about related work. We will introduce the Dino framework and describe the evaluation protocols that were used to assess it. Next, we will walk through the experiments used to compare to prior work, together with a range of ablation studies. Finally, we will conclude with a brief summary. Okay, then let us jump into the motivation. The starting point is to note that transformers have seen tremendous success in the field of natural language processing, significantly advancing performance on many tasks. Given this success, there have been various explorations of transformers in computer vision, perhaps most notably the vision transformer, or VIT, proposed by Bojanowski et al., which showed competitive performance with CNNs and the ability to benefit from large-scale pre-training. However, it did not immediately reveal any dramatic benefits that transformers would yield over CNNs in the field of vision. To understand this, the authors note that one of the key factors in the success of transformers in NLP was their use of self-supervision, with examples such as BERT making use of close completion and next sentence prediction, and GPT, which was trained in an autoregressive language modeling objective. Differently from these methods, VIT is trained in a fully supervised manner, which raises the question of whether vision transformers would also benefit significantly from self-supervision. A second observation is that transformer architectures encode a different set of inductive biases to CNNs. As one example, without convolutions, they do not enforce the principle of locality, in which computational operators only consider a local neighborhood of inputs. As a result, it is possible that transformers behave quite differently under self-supervision. For example, thanks to these different inductive biases, they may represent concepts like scene layout or object boundaries in a different way, raising the broader question of whether different properties emerge from transformers than CNNs under self-supervision. A third observation is that there have been many ideas proposed in the self-supervised literature that improve performance. Examples include momentum encoders to provide contrastive learning with more negatives and multi-crop data augmentation. We would like to understand how these components may influence the various properties of self-supervised transformer features. We turn next to related work. Dino draws inspiration for its approach for a number of previous works. Here I will discuss a few key themes. One line of work has focused on instance discrimination, much of it building on the seminal exemplar CNN paper of Bojanowski et al. In 2014. The key idea in this paper was to train a CNN to perform a surrogate task by taking patches from images with interesting gradients, such as this one, then generating many variants of the patch via aggressive augmentation. Collectively, the augmentations of a patch were treated as a single class, which a CNN was trained to discriminate from other classes. In addition to their proof of concept that this approach works well, a number of useful studies were conducted, with results such as this one, which investigated the influence of number of classes plotted on log scale versus classification accuracy on STL10 shown in blue, finding that more classes, i.e. more patches, improves performance until the task gets too hard for the model, likely due to limited model capacity. To show that excessive task difficulty was indeed a possible cause of weaker performance with many patches, the authors also plot error on validation data in red for the surrogate task, which begins to grow rapidly at the higher number of classes, suggesting that the model is at the limits of its ability. One further comment of interest here is that the authors found that the best augmentation choices for their method depend heavily on the downstream data distribution. For instance, color and contrast augmentations are much more effective than rotation or scaling when learning features for datasets like Caltech 101, which contains images that are often well aligned. But the same is much less true for datasets with less careful object framing. This work lays the groundwork for future efforts by works like Dino by noting that, in principle, their method could continue to improve if given sufficiently diverse data. A second direction in self-supervised learning, investigated by Grill et al., was to move away from instance discrimination. Under the BYOL framework, an input image is first augmented, then passed through a representation learning network and then a projection. Then a second augmentation of the same image is passed through a second network and projected with the same architecture, but different weights. Finally, a predictor is attached to the first network, which aims to regress, under a mean square error loss, the L2 normalized outputs produced by the second network from the L2 normalized targets of the first network. The first network, which is referred to as the online network, is updated via gradient descent with respect to the regression loss. By contrast, the second network, or target network, is updated as a convex combination of its current weights and those of the online network. This framework achieved strong results under a range of linear probe and downstream transfer tasks, in addition to dropping the need for negatives, and was shown to be more robust to batch size and data augmentation strategy than prior works such as SimClear. The authors suggest that it is thanks to its asymmetric weight updates, that is to say, only the online parameters are updated directly with respect to the loss, that prevents the network from collapsing to simply learning to predict a constant vector. Dino follows a similar philosophy to BYOL, but uses identical architectures for teacher and student, and employs a different loss. The Dino authors also note several distillation ideas that influence their approach. One is the noisy student framework of Xie et al. This framework begins with a labeled collection of images on which a teacher network is trained. The teacher model is then used to generate pseudo-labels on unlabeled data. Next, a higher capacity student model is trained on a combination of the labeled and unlabeled data, on which heavy data augmentation and heavy model augmentation is applied to produce a student that is more powerful than the teacher. This student is then recast as the teacher, and the process iterates. Either soft or hard labels can be used for pseudo-labeling, and here it was found that soft labels worked slightly better for out-of-domain generalization. Noisy Student achieved strong classification scores. It also demonstrated significantly better robustness to an FGSM attack than a model that did not make use of the unlabeled data. In this plot, the x-axis denotes the attack strength value, epsilon, while the y-axis denotes ImageNet top 1 accuracy. The red line denotes the model trained with Noisy Student, while the black line denotes the baseline, which is significantly less robust. Dino also aims to leverage self-distillation, but without any form of labels. A second relevant work on distillation is the co-distillation framework of Anel et al. The motivation for this work was to make better use of hardware to speed up training beyond the limits of distributed SGD, and to produce models with the performance and prediction stability benefits of ensembles without their test time complexity or multi-stage training. The framework works by training multiple models in parallel, and then requiring each model to match the average prediction of the other models. The first plot shown here depicts training step on the x-axis and cross-entropy loss on the y-axis for a language modeling task on common call data, and compares co-distillation, shown as a green line, with several baselines like label smoothing in gold and blue for different hyperparameters, single model training in pink, and traditional ensembling in red, illustrating that co-distillation does indeed perform similarly to ensembling. A second study investigated how sensitive co-distillation is with respect to prediction staleness. While there was a performance degradation if knowledge is exchanged between models too infrequently, such as every 250 or 100 steps, co-distillation with an update interval of every 50 steps works well. This suggests that the predictions used by co-distillation have much greater tolerance to staleness than gradients do in SGD. While also making use of multiple models, Dino differs from co-distillation in that the teacher is updated with a moving average of the student, rather than having the teacher also learn by distilling from the student, as is the case in co-distillation. Next, we will introduce the Dino framework. The Dino framework builds on two core ideas. The first is knowledge distillation, in which we train a student network, here denoted G theta S, to match the outputs of a teacher network, G theta T. Theta S and theta T indicate their respective parameters. Since we are operating without labels, we do not use direct supervision to guide the teacher. Instead, we begin with an input image, X. We apply one augmentation and pass it to the student. Then we apply a second augmentation and pass it to the teacher. The teacher outputs are centered so that they have approximately zero mean. Then, both the student and teacher outputs are passed through a softmax so that they each produce a distribution over k categories. The student parameters are optimized to minimize the cross-entropy between its predictions and those of the teacher. One extra key detail is that gradients are not backpropagated through the teacher thanks to the use of a stop gradient operator, noted here as SG. Instead, the teacher's parameters are updated using an exponential moving average of those of the student. Okay, there's a lot going on here, so let's unpack each of these components in a bit more detail. We noted that the student distribution is produced by a softmax. That's defined as follows. Here, tau s is a temperature hyperparameter controlling the sharpness of the softmax. Similarly, the teacher distribution is also produced by a softmax, with its own temperature hyperparameter, tau t. As we saw, a cross-entropy loss is placed between these softmax distributions to encourage them to match. This is defined in the familiar manner, with HAB equal to minus A log B. This loss is minimized with respect to the student parameters rather than those of the teacher. To make these steps more concrete, the authors provide pseudocode for an implementation of the setup we have just described. Note that this is the case for just two views of the input image, rather than using multiple crops, which is an extension we will discuss shortly. The inputs are GS and GT, the student and teacher networks, C, a value that represents an exponential moving average of the outputs of the teacher, TPS and TPT, the temperature hyperparameters for the student and teacher, and finally L and M, which are the momentum rates used in the updates for the exponential moving average of the teacher's parameters and the center value C. At initialization, the teacher and the student parameters are identical. Then, training proceeds by loading mini-batches of n images. Each mini-batch is transformed with two sets of data augmentation to create two views, x1 and x2 of the images in the mini-batch. These are first passed through the student, which will produce outputs S1 and S2 of size n by k for both x1 and x2. Similarly, x1 and x2 are passed to the teacher to produce a second pair of n by k outputs, here denoted T1 and T2. A cross-entropy loss is applied symmetrically across the different views, i.e. between T1 and S2 and between T2 and S1. To compute the two components of this symmetric loss, we first detach the teacher to prevent gradients flowing back through it, then apply a softmax to the student outputs using its temperature hyperparameter, and to the teacher outputs using both centering with a value of C and its temperature hyperparameter, before computing the cross-entropy value. Once we have the loss value, we apply backpropagation, which will flow only through the student network due to the stop gradient operator enforced by detaching the teacher. We next apply our updates, starting with an SGD step for the student parameters using gradients in the loss. Then we update the teacher as a convex combination of its current weights and those of the updated student. And finally, we update the value of C as a convex combination of itself with the average teacher outputs across both views. In practice, more than two views of each image can be used by employing a multi-crop strategy, such as that used by Suave. In particular, the set of views, V, passed to the model consist of two global views, denoted x1g and x2g, in addition to several local views at smaller resolution produced by cropping. The teacher receives only the global views, whereas the student receives local and global views as inputs. This strategy encourages the student to learn representations that capture local to global correspondences, a useful property for downstream tasks. The actual loss minimized is therefore the following, where the images passed to the teacher are the global views, while the images passed to the student are both local and global. In this work, global views consist of square crops at 224 pixel resolution, spanning more than half the image area by default, while local views are square crops at 96 pixel resolution, spanning less than half of the area of the image. A natural challenge for this distillation setup is that we don't have access to a supervised teacher. Instead, the teacher is constructed from past iterations of the student, and it is found through experimentation that using a momentum encoder with an exponential moving average works particularly well. In particular, the update rule for the teacher is to increment its parameters as a convex combination of the current values and those of the student parameters, where lambda is set to follow a cosine schedule similarly to BYOL, ranging from 0.996 to 1 across training. One point noted here by the authors is that the role of the momentum encoder in Dino is quite different to its role in MoCo, where it is used to provide a queue of samples that are compatible with the current visual encoder. In Dino, its role may be closer to that of mean teacher, where a strong model is produced by ensembling the parameters across multiple model instances. As a result, similarly to Ruppert Polyak model averaging across parameters, which has been shown to improve performance, the momentum encoder produces a teacher that performs better than the student throughout training, and as a result, is able to guide it with higher quality representations as supervision. Turning to network architecture, the network G consists of a backbone, F, for which VIT and ResNet are investigated here, and a projection head, H. Together, these are composed together to form G. After training, the features produced from F are then used for downstream tasks. The projection head is a 3-layer MLP, similarly to that of Suave, comprising a 2048-dimensional hidden layer with L2 normalization and a fully connected layer with weight norm that has an output of k dimensions. Note that unlike prior methods such as BYOL, no predictor is used, resulting in identical networks for the teacher and the student. Finally, Since VIT architectures do not use batch norm by default, a Dino model trained with a VIT backbone is also completely free of the tyranny of batch norm. One of the key challenges associated with training self-supervised methods like Dino is the question of how to prevent representation collapse, in which the outputs of the model become a single vector that trivially satisfies the loss function. A number of different mechanisms have been explored to prevent this collapse from happening, which include the use of a contrastive loss, clustering constraints, the use of a predictor subnetwork in combination with batch norm, and alternative variants that replace batch norm with other normalization strategies like group norm and weight norm. The authors find that Dino works well with using a combination of a centering operation and sharpening on teacher outputs to prevent collapse. In effect, this approach trades stability in exchange for reduced dependence on the batch being processed. In particular, centering, different from batch norm, only depends on first-order batch statistics. This centering operation can be interpreted as simply adding a bias term to the teacher outputs. The center, C, itself is updated via an exponential moving average, so it works well across different batch sizes. The moving average is defined as follows, where M is a rate parameter controlling the momentum, and B is the batch size. Sharpening of the outputs is achieved by using a low softmax temperature for the teacher. Dino conducts experiments on a number of different vision transformer configurations. For these, it follows the implementation of DEIT. In particular, the authors consider 5 networks, a ResNet 50 baseline, and 4 VIT models. Each transformer uses 12 blocks, while the channel dimension used for the learned representation varies across architectures. The larger models based on VITB use 12 heads rather than 6 in the multi-headed attention. The length of the token sequence depends on whether the size of pixel patches fed into the models are 16 or 8. In terms of parameters, the VITB model has roughly 4 times as many as the VITS variants. With regard to practical runtime speed, all VIT models are slower than the ResNet, and the largest VITB8 model is roughly 20 times slower, as measured on an NVIDIA V100 GPU. As with prior works, a CLS token is used to aggregate information across the sequence. To this we attach the projection head, H, which takes the form of the MLP we discussed previously. The pre-training procedure proposed by Dino is performed on ImageNet without labels. The models are optimized using AdamW with a batch size of 1024 across 16 GPUs for the smallest VIT model. Dino uses linear scaled learning rate warm-up and then decays the learning rate with a cosine schedule. The weight decay also follows a cosine schedule from 0.04 to 0.4. The temperature of the student, tau s, is set to 0.1, while the temperature of the teacher, tau t, is warmed up linearly from 0.04 to 0.07 over the first 30 epochs. This lower teacher temperature corresponds to the sharpening concept discussed previously. BYOL data augmentation is used, which include operations like color jitter, Gaussian blur, and solarization. Finally, as with prior works, bicubic interpolation is used to adapt the position embeddings across different scales. If you want to dig deeper into the nuts and bolts, the trained models and code associated with this work are available on GitHub. Let's turn next to the issue of evaluation. Typically, self-supervised features are evaluated in 2 ways, via linear probes on frozen features and via fine-tuning. For the linear probe protocol, data augmentation is used in the form of random resize crops and horizontal flips to train the linear probe, while evaluation is performed on a central crop. For the fine-tuning protocol, the network is initialized with weights from Dino pre-training and then adapted using labels on the downstream task. The Dino authors note that both these protocols are quite sensitive to the choice of hyperparameters used. Consequently, they also evaluate under a k-nearest neighbors protocol in the style of Wu et al. For this, the pre-trained model is frozen and used to compute features for each image among the training set of a given downstream task. Then, a nearest neighbor classifier is built using the k-nearest neighbors on the training set to assign a label to the test image by voting. To implement this protocol, the authors sweep over various numbers of nearest neighbors, finding that 20 works well in practice. An advantage of the k-nearest neighbor protocol is that it requires no other hyperparameters or data augmentation beyond the value of k, and it only requires one pass over the downstream dataset, which simplifies the evaluation procedure considerably. We can look at these evaluation protocols in a little more detail, starting with the weighted k-nearest neighbors evaluation protocol. First, features are computed for the training data associated with a downstream task with the pre-trained model frozen. We classify a test image, denoted x, by comparing its features against those of the training set, here denoted by t. The feature representation of each image is taken to be the output of the CLS token, which is 384-dimensional for VIT-S and 768-dimensional for VIT-B. Given these features, the top k nearest neighbors in the training set, denoted nk, make a class prediction for the test image by voting. This is done by assigning to class C a value comprising the weighted sum of the votes. Here, the contribution weight alpha I for each neighbor is defined via scaling the similarity of the features and passing the results through an exponential. The temperature scaling hyperparameter tau is set to 0.07, following Wu et al. As noted previously, it is found empirically that a value of k equals 20 for the neighborhood size works well, and so this is used throughout the experiments. The linear classification protocol is slightly more involved. The projection head is removed and a linear classifier is trained with SGD on frozen features with a batch size of 1024 for 100 epochs on ImageNet. No weight decay is applied to the classifier, and for each model the learning rate is set by a hyperparameter sweep. During training, as noted previously, random resize crops and horizontal flips are used, while during testing, central crops are used. To evaluate linear probe performance for VIT models, the Dino authors adapt the strategies that have been developed in other contexts. For the VIT-S model, it is found that a feature-based evaluation in the style of BERT works well. This is achieved by concatenating the CLS tokens from the last layers of the model. The authors experiment with using the last 1, 2, 4, or 6 layers, which correspond to total representation dimensionalities of 384, 768, 1536, and 2304. Of these, it is found that using the last 4 layers works particularly well. For VIT-B, there was no gain to using CLS tokens from additional layers, so instead, only the last layer is used. It is found, however, that an approach inspired by CNN evaluations, in which the CLS token is concatenated with the global average pooled output across each patch token, which doubles the dimensionality of the representation, yields a small gain in performance. We come now to the experiments. The first set of experiments were conducted on ImageNet, comparing Dino to existing self-supervised methods with the same architecture under linear probe and k-nearest neighbor evaluations. The starting point here is a supervised ResNet 50 trained with the optimization recipe and aggressive data augmentation employed by the DEIT authors. This model attains 79.3% accuracy. Here, the param column indicates model parameters in millions, while the images per second column indicates the model throughput on an NVIDIA V100 GPU with a batch size of 128. As self-supervised baselines, comparisons are provided with SimClear, Moco V2, InfoMin, Barlow Twins, Online Bag of Visual Words, BYOL, Deep Cluster V2, and SWAV. In this setting, it is found that Dino performs similarly to SWAV under a linear protocol and slightly better under a k-nearest neighbor protocol. The key takeaway here is that for ResNet 50, Dino is competitive with the best prior work. A second set of comparisons were then made with a VITS architecture, comparing again to a strong supervised baseline. This model has a comparatively similar number of parameters, throughput, and accuracy to the ResNet above. The Dino authors compare against BYOL, Moco V2, and SWAV as baselines. Against these, Dino offers a significant boost in performance for VITS, especially under the k-nearest neighbor evaluation. It's particularly notable that the linear probe and k-nearest neighbor scores have a relatively minor gap for VIT, which is quite different from the ResNet 50, in which the linear probe scores exhibit a major gap over the k-nearest neighbor scores. A second comparison investigates the performance of Dino across different architectures. Here, the goal is not necessarily to make an apples-to-apples comparison, but rather to explore the potential that Dino has to yield improvements across different VIT settings. First, when comparing to chunkier ResNets trained with SimClear, SWAV, and BYOL, Dino performs favorably when using a VITB16 model with a roughly similar throughput and number of parameters. Comparing again to SWAV and BYOL with chunkier backbones, Dino in combination with VITS on a patch size of 8 attains similar linear probe accuracy, but much better k-nearest neighbors performance. A final comparison with SimClear V2 on a chunky ResNet 152 model against Dino on VITB8 also demonstrates the potential of Dino to obtain gains in linear probe performance from additional parameters, although k-nearest neighbor performance drops here slightly. These comparisons indicate that reducing the patch size brings a significant gain at the cost of lower throughput. In fact, reduced patch size brings a major gain even when the overall number of model parameters is reduced by a factor of 4. The next set of experiments aim to dig a little deeper into the properties of the VIT features trained with Dino. Since the results on ImageNet were particularly promising under a k-nearest neighbors evaluation, the Dino authors next consider the task of image retrieval, where they evaluate on the revisited Oxford and Paris retrieval datasets. In this comparison, results are reported on the medium and hard splits of these datasets, which correspond to evaluating on various combinations of images that capture landmarks from challenging viewing conditions. Comparisons are first made with strong features from a supervised baseline trained with a listwise loss, as well as features from a supervised VITS16 model trained on ImageNet. Dino performance is reported with a ResNet 50 architecture and a VITS16 architecture, both yielding gains over the supervised VIT baseline. In each case, evaluation is performed by freezing the features and applying k-nearest neighbors directly for retrieval. One advantage of self-supervised methods is that they can be trained on any dataset without labels. The Dino authors make use of this fact to retrain Dino on the clean subset of 1.2 million images from Google Landmarks dataset v2. These are images that are particularly well suited to learning landmark retrieval features, and they bring a further significant boost, outperforming previous off-the-shelf descriptors. The next experiment considers the copy detection task, in which the aim is to recognize images that have been distorted in some way, typically by blurs, insertions, and other modifications that mimic attempts to avoid detection of copyright infringement. The benchmark used for evaluation is the copy days dataset, and in particular, the strong subset, which contains particularly aggressive distortions. To enable comparison with previous work, 10,000 distractor images are added by randomly sampling from YFC 100M. The copy detection process is implemented by directly evaluating cosine similarities between features produced by the network, where the features are obtained by concatenating the CLS token with gem-pooled patch tokens, and applying whitening on the resulting features, where the whitening transformation is learned on an extra 20k random images from YFC 100 million. Comparisons are made with the multigrain model on both 224 pixel resolution and higher resolution images, as well as with a supervised VITB16 model. Against those baselines, Dino features at 224 pixels and 320 pixels perform strongly, suggesting that they are well suited to this task. The next experiments investigate the ability of Dino to segment an image. First, qualitative results are provided that examine the self-attention maps produced by the CLS token on heads from the last layer of VITS8. We find remarkably clean segmentations of a bird, a toothbrush, a boat, and a bike. The model also appears to segment the UK Houses of Parliament, giraffes, a dog taking some downtime, and a small aircraft. Notably, these attention segmentations appear to be class-specific. They capture both giraffe instances, but not the toothbrush and the toy, for example, although both could be considered salient. To quantify this segmentation ability, evaluations were conducted for the task of video instance segmentation on Davis 2017. The protocol used here is to segment scenes by propagating masks using nearest neighbors between frames. Here, results with frozen Dino features are compared with existing methods, and the metrics used to evaluate performance are mean region similarity and mean contour based accuracy, which collectively assess the quality of the segmentation. The frame resolution for these experiments is 480 pixels. To provide reference numbers, the performance of supervised baselines using VITS8 features trained on ImageNet, as well as the supervised STM video object segmentation model are reported. Comparisons are also provided against self-supervised baselines like cyclic consistency, the memory-augmented self-supervised tracker, and spacetime correspondence. Note that the latter two of these baselines use lightweight ResNet 18 architectures. Dino trained on ImageNet with VITS16 and VITB16 attains reasonable performance, and sees a substantial gain when switching to smaller patch sizes with VITS8 and VITB8. One takeaway from these experiments is that since Dino is evaluated without fine-tuning, the learned features must have retained some form of spatial information. To dig deeper into the information contained within the self-attention maps of Dino, the authors next visualize self-attention from the CLS token from the last layer of VITS8, this time colouring the attention of different heads with different colours. We observe that Dino is able, to some extent, to perform a kind of semantic segmentation of vegetables and slightly less healthy food, a tower and a small flag fluttering above it, and a boat near a river dwelling. For this animal, we see a successful segmentation of the bridle, but an over-segmentation of the neck, likely due to the abrupt change of colour. In this image, we see a robust segmentation of a bush in the background, despite the fact that it is heavily occluded. Other examples include a truck and a teddy bear. To compare the attentions that emerge from Dino with those of supervised transformers, a further visualization is provided by thresholding the self-attention maps of the CLS token in such a way that 60% of the attention mass is preserved. It is found that supervised VIT produces a very noisy segmentation, while Dino achieves a much cleaner grouping of pixels into coherent regions. To quantify this more precisely, the thresholded masks are compared via Jacquard similarity to the ground truth masks on Pascal VOC 2012. When comparing the attentions from a randomly initialized model and a supervised model with Dino, we see significant improvements are achieved by Dino for both VIT S16 and VIT S8. The Dino authors note that it is possible to obtain reasonable segmentations from self-supervised CNNs rather than transformers, but we typically need dedicated methods based on gradients and attribution propagation to obtain good results. To gain a further sense of how this self-attention mechanism of Dino behaves, the authors provide visualizations for sets of reference points from the self-attention block at the last layer of VIT S8 model trained with Dino. For example, given this image of healthy nutritional items, the self-attention on the bottle highlights the other bottles, the labels highlight the other labels, the Guinness logo appears to focus heavily on the remaining part of the Guinness logo, while this banana pixel attends to other banana pixels. In a second example, we find that selecting reference points on the cup produces quite different results to selecting a nearby pixel in the drink itself. Selecting a pixel on this device similarly highlights the object, as does selecting one of the scissor blades, albeit that it produces a slightly less clean segmentation. A final example illustrates that selecting a reference point on the blurry elephants in the background separates them from the foreground zebra, which can itself be segmented by an appropriate reference point. As a further visualization, each ImageNet class is represented with its average feature across the validation images. These features are reduced to 30 dimensions using PCA, upon which t-SNE is run for 5,000 iterations with a perplexity of 20 and a learning rate of 200. Here are the results. There are a lot of ImageNet classes, so we can zoom in to get a better idea of what is happening. Here we can see, for example, a tight clustering of bird categories. In this region, we see snakes grouped together, while here we can see vehicles. More broadly, the visualization suggests that Dino is doing a good job of grouping related concepts into coherent clusters. In order to provide a more comprehensive evaluation of the Dino features, they are compared for transfer learning against supervised features using the same architecture that has been trained with ImageNet labels. The particular transfer learning protocol employed is that of the DEIT authors, which compares features across 8 tasks. The particular tasks considered are CFAR 10, CFAR 100, iNaturalist 2018, iNaturalist 2019, Oxford 102 Flowers, Stanford Cars, and ImageNet. For both VIT S16 and VIT B16, we find that Dino brings a consistent gain over the supervised baselines. This is consistent with prior work observing that self-supervised features appear to transfer better than supervised features. Note that Dino attains particularly notable gains on ImageNet itself, boosting supervised performance by 1 to 2%. The next experiments examined the performance of Dino features for low-shot learning on ImageNet. This is done by training a logistic regressor with the SICON library on frozen Dino features using either 1% or 10% of the training set labels. Comparisons are made with self-supervised pre-training and fine-tuning methods like unsupervised data augmentation, SimClear v2, BYOL, and SWAV with ResNet 50, as well as SimClear v2 and BYOL with chunkier models. Numbers are also provided for semi-supervised methods like SimClear v2 with knowledge distillation, SWAV with contrastive semi-supervised learning, FixMatch, meta pseudo-labels, and SimClear v2 with knowledge distillation on a chunkier model. In comparison to these approaches, it is found that frozen Dino features without data augmentation perform on par with existing models that use a similar number of parameters, but make use of semi-supervised learning. We now come to the ablations. The first ablation studies concentrate on identifying which of Dino's components contribute to its performance. For this, the authors train a VITS-16 model with self-supervision for 300 epochs, switching on and off various components. The column headers here represent momentum, use of sinkhorn NOP, use of multicrops, whether a predictor is attached to the projection head, and linear probe accuracy. A first observation is that, relative to Dino, removing the momentum completely degrades the performance. Note that it is possible to train without momentum and avoid collapse if sinkhorn NOP is used, and in fact, this recovers the SWAV method, though its performance is worse than Dino. Using both momentum and sinkhorn NOP adds little benefit, and in fact slightly degrades performance. Removing the multi-crop pre-training, or using mean square error rather than cross-entropy, also substantially harms performance. It is further found that adding a BYOL-style predictor brings no benefit to Dino. Other methods, such as BYOL and MoCo v2, can also be interpreted with respect to these components, the latter of which uses the info-NCE loss. Both underperform Dino here. To provide a more complete picture of the differences between Dino and these alternative baselines, each method is applied to both a ResNet 50 and a VITS-16 for 300 epochs on ImageNet. When comparing performance with a ResNet 50 architecture, Dino performs well, but still somewhat similarly to the baselines. With VITS, however, the performance gain is substantial, especially under the k-nearest neighbor evaluation. A takeaway here is that Dino is particularly effective for self-supervised training of vision transformers. To further tease apart the differences between the methods, a more detailed breakdown is provided to analyze the role of components on top 1 linear probe accuracy that differentiate Dino from MoCo v2 and BYOL. Here we additionally consider the influence of the centering operation used by Dino, as well as the use of batch normalization in the projection heads, and their role in combination with a student predictor subnetwork. Compared to Dino, switching to a mean square error loss still works, but harms performance. This trend also occurs when considering Dino without multicropping, which is much weaker, and switching again to a mean square error loss. Note that unlike the cross-entropy loss used in Dino, no sharpening is applied to the mean square error loss. As noted previously, adding a student predictor has minimal effect, but when considering BYOL, removing the predictor causes learning to collapse. This finding is consistent with the observations of the BYOL authors. It appears that using centering without a predictor is sufficient to avoid a collapse with BYOL, though it works less well. It is further found that multi-cropping also works pretty well with MoCo v2, improving a baseline by 2%. Removing this component harms performance in Dino. By contrast, multi-cropping does not appear to help BYOL. To better understand the relationship between Dino and Suave, an ablation is conducted to explore the effect of momentum and the teacher output operation. We look first at the influence of the operator applied to the teacher's outputs to prevent collapse. Compared to Dino with momentum using a simple centering operation, using a softmax along the batch axis, or synchron-nop, performs similarly, at the cost of some extra complexity. When momentum is removed, however, centering is no longer sufficient, and either the softmax or synchron-nop are needed, with the latter representing the Suave method. Overall, momentum makes a substantial difference to performance. To clarify what is meant by the softmax batch operation described above, we can look at the implementation of synchron-nop used in Suave. Given an input x of size n by k and tau, the synchron regularization parameter, x is first divided by tau and exponentiated. Then, for each synchron iteration, we sum the mass along each feature and use it to normalize x. Then we sum the mass along each sample and use it to normalize again. When performing only a single iteration of synchron, we can simplify this code to produce the softmax variant, in which we simply apply a softmax along the batch dimension, then normalize with respect to the sample masses. As seen in the table above, this approach is competitive with the full synchron process used by Suave. The next ablation looks at how the choice of architecture affects k-nearest neighbor performance relative to linear probe performance. For this, we evaluate frozen features from ResNet 50 and VITS trained with Dino with both linear probes and k-nearest neighbors. For this experiment, no data augmentation is used when extracting the features. We begin by comparing the two models and computing the delta between their scores under a linear probe for the full ImageNet dataset, as well as variance with 10% and 1% of the data. Similarly, we train probes with 10% of the Places 205 dataset and 1% of this dataset. Finally, probes are trained for Pascal VOC 2007 and Oxford Flowers 102. The average advantage of VITS over ResNet 50 is 2.4 percentage points. However, when we examine the same experiments under a k-nearest neighbor evaluation, we see a much greater average difference of 5.6 percentage points between the architectures. These results confirm the previous observation that Dino combines well with the VIT architecture to produce features that seem to be particularly well suited to k-nearest neighbor classifiers. A further topic of interest is the influence of self-supervised pre-training on the fully supervised ImageNet performance of VITB16 models. Comparisons are made with several baselines. One thing to note here is that the models differ in their image resolution as well as their supervised training procedure, both of which make a big difference to performance, so we have to control for this factor. One set of baselines extend the pre-training data to include the JFT 300 million dataset, which can be used either in an unsupervised way with masked patch prediction or by using labels. A second baseline makes use of an additional model, in this case a supervised RegNet Y. Finally, the third set of baselines do not use additional data or a model. Random initialization, followed by training with the VIT training procedure, attains 77.9. Random initialization with the DEIT training procedure attains 81.8. Using supervised pre-training, which effectively extends the training schedule, brings little benefit. By contrast, Dino leads to a boost in performance. The next ablation compares the k-nearest neighbour performance of Dino with VITS and VITB at different patch sizes. The results are depicted here, where the x-axis denotes throughput in images per second, and the y-axis denotes ImageNet top 1 accuracy. Starting from the VITS model with 16 by 16 patches, we see that decreasing the patch size to 8 by 8 brings gains, which are further improved by reducing the patch size to 5 by 5. Similarly, for VITB, decreasing the patch size from 16 by 16 to 8 by 8 brings a boost. In each case, it's quite interesting to note that the gains from reduced patch size involve no extra parameters, but they do correspond to substantially lower model throughput. For example, moving to 5 by 5 patches drops the throughput to 44 images per second rather than the 180 images per second attained for 8 by 8 patches. Much like other self-supervised approaches such as SimClear, Dino benefits from training with a projection head. The projection head follows a design inspired by the SWAV approach. It uses an n-layer MLP in which each hidden layer has 2048 dimensions and Gaussian error linear units. The last layer has no GELU. Its outputs are L2 normalized and then passed through a final weight normalized fully connected layer. No batch norm is used in the Dino VIT projection heads. Since VIT does not use batch norm, this means that the whole system is batch norm free. To justify this design choice, VITS is trained for 100 epochs on ImageNet, where it is found to perform better without batch norm under a k-nearest neighbours evaluation. In addition to improved performance, this has the added benefit of being simpler and having no need for batch norm synchronization, which is typically required to get the most out of batch norm, but slows things down. The next study explores possible design choices for the projection head itself. One variant considered does not use an L2 normalization bottleneck. The input is an image, X, which is processed by the backbone, F, and then fed into the projection head, which consists simply of an n-layer MLP that outputs k dimensions. A second variant does include an L2 normalization bottleneck. As before, the input is an image that is fed through the backbone. This time, however, the n-layer MLP is followed by L2 normalization and an additional linear layer. These two designs are compared for Dino VITS16 on ImageNet with an output dimensionality of 4096, with different numbers of linear layers in the projection head. It is found that with L2 normalization, the projection head benefits from using 4 linear layers. By contrast, without L2 normalization, the model doesn't train with more than 2 linear layers without collapsing, and with just 2 linear layers, the performance is much weaker. Our takeaway here is that L2 normalization bottleneck in the projection head is essential. We next compare the effect of different projection head output dimensions. For the configurations considered here, the L2 normalization bottleneck dimension is set to 256, which limits the overall number of parameters. A range of different output dimensions are considered, of which 65,536 performs best. The takeaway here is that using a large dimensionality helps, but only up to a point. Finally, we compared different choices of activation functions for the projection head. Note here that in VIT, Jégou is used by default. To explore options, a VIT-S model is trained for 100 epochs using either Jégou in the projection heads or ReLU in the projection heads. It is found that Jégou works quite a lot better, so the reasonable takeaway here is that Jégou is preferable for projection head. The next ablation studies look at the role of the teacher. First, note that various strategies can be used to build the teacher from the student. To compare them, performance is reported for ImageNet top 1 accuracy with k nearest neighbours. One strategy simply uses a copy of the student as the teacher. This does not work. Neither does using the previous iteration of the student. However, using the previous epoch of the student as the teacher does work, although it still lags far behind using a momentum teacher. The fact that using a previous epoch works suggests that there may be room to explore alternative teacher designs. A second study looks at training dynamics. This plot depicts the evolution of performance for the student and the teacher with a VIT architecture. The x-axis depicts epochs, and the y-axis depicts ImageNet top 1 accuracy. We observe that the teacher always outperforms the student, a trend that is preserved when a ResNet 50 architecture is used instead of a VIT architecture. The Dino authors interpret the momentum teacher in Dino as a form of Polyak-Ruppert averaging. In essence, Dino is using model ensembling as a way to provide higher quality predictions to guide the student. The next ablation study looks at the issue of collapsed representations. There are two forms of collapse that typically arise during pre-training. The first is a collapse to a uniform output along dimensions. The second is collapse to a vector that is dominated by only one dimension. In the Dino framework, the centering operation acts to avoid collapse along one dimension, but encourages uniform outputs, while sharpening discourages uniform outputs, but encourages collapse along one dimension. These complementary roles can be seen by decomposing the cross-entropy term between the distributions as follows. Note that when the KL term on the right is equal to 0, the two distributions have become identical. Since the teacher is built from the student, this indicates the outputs are constant, so a collapse has occurred. To analyze this effect quantitatively, we can plot the entropy of the teacher outputs during training. Here the x-axis denotes epochs, and the y-axis denotes the entropy of the targets produced by the teacher. The blue line indicates the use of sharpening, the red dashed line indicates the use of centering, and the orange line indicates the use of both in combination. We can also plot the KL divergence between the teacher and the student, with the KL divergence quantity indicated on the y-axis. From the left plot, we see that the entropy of the teacher converges to 0 without centering, or to minus log 1 over k without sharpening. We also see from the plot on the right that the KL divergence between the teacher and student converges to 0 unless both operations are used. This analysis suggests that the two operations of centering and sharpening balance each other out to prevent collapse. The next ablations look at various optimization hyperparameters and model properties, starting with the influence of the momentum hyperparameter in the updates to the center term for Dino. Several choices of momentum are considered, where it is found that 0.9 works best. Interestingly, we observe a collapse when the centering update is too slow. Next, the influence of the teacher softmax temperature tau t is studied. By comparing different values, it is found that the temperature needs to be 0.06 or lower in order to prevent collapse. However, the authors also find that they can avoid collapse by doing 30 epochs of linear warm-up from 0.04 to 0.07, which yields slightly better performance. The next study looks at the influence of training the model for more epochs, which has been found to consistently improve performance in prior work. Here, the authors train VITS for 100, 300, and 800 epochs, finding that the 800 epoch model strongly outperforms the shorter training runs. One point the authors note here is that for their implementation of BYOL, performance got worse beyond 300 epochs. So, for the main comparison between Dino and other self-supervised methods we saw previously, BYOL is reported with 300 epochs of training, while the other methods like Dino, Moco V2, and Suave are reported with 800 epochs of training. Next, we compare differences between supervised and self-supervised attention maps for the purpose of segmentation. Here, the evaluation is conducted on Pascal VOC 2012, and thresholding is applied to these self-attention maps to produce masks that capture a fixed percentage of the mass. These masks are then compared to the ground truth masks, and their quality is assessed via Jacquard similarity. We first find that random weights are less effective than supervised training, as expected. We observe a significant boost when moving to self-supervised methods like Dino, even without multi-cropping. Other self-supervised methods like Moco V2, BYOL, and Suave also perform well, with BYOL attaining the best scores overall. The takeaway here is not that any particular method of self-supervision enables segmentation, but rather that the combination of self-supervision with the VIT backbone appears to work well for segmentation. Finally, we study the influence of the number of VIT heads on both accuracy and model throughput. Here, the evaluation is performed with k-nearest neighbor classification. Starting from 6 heads, performance gradually improves with 8, 12, and 16 heads, at the cost of reduced throughput. For all other experiments, 6 heads are used by default, a choice that offers a reasonable trade-off between efficiency and accuracy. One component that plays an important role in Dino is the multi-crop strategy. This is implemented using the PyTorch random resize crop function by selecting a scale hyperparameter S, then sampling 2 global views between S and 1 and resizing the results to 224 pixels, then sampling 6 local views with scale between 0.05 and S and resizing the result to 96 pixels. The authors note here that the choice to use non-overlapping scale ranges is somewhat arbitrary, following Suave, and could probably be improved. Across various choices of the S hyperparameter, it is found that somewhere around 0.3 works well. One point to note here is that this value is higher than the parameter choice used in Suave, which was 0.14. The next study implements multi-cropping with the VITS16 backbone, trained for 300 epochs for various self-supervised frameworks. Each is compared with either 2 global crops or 2 global crops together with 6 local crops. The frameworks considered are BYOL, Suave, Moco V2, and Dino. A first observation is simply that multi-crop does not benefit all frameworks equally. In particular, while Dino sees a major boost, BYOL actually does worse when using both global and local crops. The Dino authors conducted an investigation to see what is happening with BYOL, with and without multi-cropping. This plot shows what happens, with epochs on the x-axis and k-nearest neighbor top 1 accuracy on the y-axis. The multi-crop BYOL variant shown here in orange starts out strongly, but then appears to degrade in performance. It was found that this behavior was consistent across a wide range of hyperparameters, and also occurred when using ResNet 50 rather than VITS. Since it was not the main focus of this paper, the Dino authors did not pursue this further. To give some sense of the computational burden associated with Dino, the authors measured the time and GPU memory required to run VIT-S16 on 16 GPUs across two 8 GPU machines. Here, top 1 accuracy is reported under a linear probe evaluation on ImageNet for a baseline using only global views, as well as variants that use 2, 6, and 10 local views. In addition to bringing overall improvements in performance, we can see that multi-crop improves the accuracy running time trade-off. For instance, we can obtain 72.5 top 1 accuracy in 45.9 hours, but we can obtain a much better accuracy of 74.6 in just 24.2 hours when using multi-crop, albeit with an increase in GPU memory from 9.3 gigabytes to 15.4 gigabytes. Since even with additional epochs, the global view model does not match the variant with crops, the results support the view that local to global augmentation is valuable. We can also see that the gains due to additional local views see diminishing returns. For instance, accuracy improves from 75.9 to 76.1 when moving from 6 local crops to 10. The next study investigates the influence of batch size on feature quality. For this, the features are evaluated for their ImageNet top 1 accuracy with k nearest neighbours after 100 epochs of training without multicrop. To alter the batch size, the learning rate is scaled linearly, following Goyal et al. The results, shown here, suggest that Dino still works well with smaller batch sizes. For the smallest batch size of 128, it is likely that retuning of hyperparameters like momentum mates would be required to ensure that training is performed optimally. One point to note here is that this robustness to batch size differs from contrastive approaches, for which the batch size is critical. Okay, let's wrap things up with a summary. This work introduced Dino, which can train a vision transformer with self-supervision to reach a performance comparable to the best complets that are trained for this scenario. We saw that 2 additional properties emerge from Dino, namely high-quality features for k-nearest neighbor classification and features that contain information about scene layout, opening the door to applications such as semi- or weakly supervised segmentation. More broadly, the authors suggest that Dino may provide a route towards building a BERT-like model on top of the vision transformer architecture. Plans for future work included an exploration of self-supervised pre-training on uncurated images, and indeed, a follow-up paper from Goyal et al. Investigating this direction appeared on arXiv earlier this year. I recommend taking a look at this paper for an interesting collection of experiments continuing the same research theme. That's it. We have reached the end. Thank you for your attention.